So this is our experimental setup where you can see our induction motor is coupled with DC generator. In this setup we are doing the fault diagnosis of the induction motor. Now currently the induction motor is loaded with broken rotor fault, and we will see how the broken rotor fault is identified through the digital twin. This is the control panel where you can see there is a variable frequency drive. Here we will set the frequency to 50 Hz and start the motor. Now you can see the motor is started and it is now currently operated at 50 Hz. These are 3-phase current outputs, voltage. You can see this is the RPM of the motor. Now currently the motor is running at no load, so you can see it is 1499 RPM. In this section you will see the supply voltage, field voltage and field current of the DC generator, and here there is a part of load box where we can vary the load between 0 to 22 kilowatt at different settings, and the load box is present here. Now this is the supply, 3-phase supply to the induction motor. We have clamped the current sensor at the Y phase, and the current sensor is connected to the digital twin through a signal conditioning circuit, which is responsible to collect the current signature in real time. This is the digital twin of induction motor. You can see the motor is at running condition. Now we will collect the current in real time and do the diagnosis. You can see in real time the current is collected. You can see the phase current is 16 ampere, fundamental frequency is 50 Hz, the amplitude of fundamental is 3191. It is completely matching with the current generated in the experimental setup as well. Now after the calculation of fundamental frequency, the digital twin generated two side bands, which is 57 Hz and 42 Hz, and indicate the presence of broken rotor bar fault, which was experimentally loaded in the induction motor.